Okay, I guess we can start. So welcome everyone, and today we are happy to have Indranil Halder. Sorry if I don't pronounce it perfectly. And the talk is going to be about closed string origin of thermal entropy.
Thank
Please
you
go.
so much. I thank the organizers for giving me this opportunity to present my work here. So today's talk is about microstates of black holes, and emphasis is going to be on non-zero temperatures. Before we get into non-zero temperatures, let's review quickly the available techniques at hand. So first approach is based on holography. So in holography, what we do is we, let's say, put some number of branes in flat space, and then we take a decoupling limit. And because we have to take decoupling limit, we are necessarily stuck into strong weak sector of the duality. So for example, when the boundary CFT is weakly coupled, our gravity theory is strongly coupled. On the other hand, when the gravity is weakly coupled, the CFT is kind of out of hand. So unless you have some sort of protection in your calculation like supersymmetry, the calculations that you do on one side is not going to be under control. And we all also know that if we turn on non-zero temperature, then it's not possible to have supersymmetry, at least when all the fields are real in suitable sense. So for thermal entropy, this approach is not going to be very fruitful. Another approach to microstate counting is due to discussion of topological strings. So when we discuss topological strings, let's say on a Calabi-Yau threefold, then the result depends only on the half of the moduli of the Calabi-Yau threefold. For instance, if you are in type 2a frame, then the answer is only going to depend on Kähler moduli. It's going to be insensitive to complex structure moduli. Therefore, if you use topological strings to discuss microstates, then the answers are going to be only valid when the answer is captured by half of the moduli, which in supergravity language is related to attractor mechanism, and that's again related to supersymmetry. Therefore, any approach based on topological strings is also not going to work for finite temperature discussions. So now we face this problem of uh, creating a new formalism within string theory that would allow us to discuss thermal entropy of black holes. So what are the possible directions that we can go? The first, let's try to review the statement of the problem carefully. So suppose we are in supergravity and we have a black hole solution. We want to calculate its thermal entropy. The calculation one when one does this calculation, one can see that the entire contribution is coming from boundary terms in target space. For instance, this is related to the fact that the Hamiltonian is a boundary term, and so if you have, let's say, Einstein-Hilbert term, and you are trying to calculate the black hole entropy, then the only contribution from Einstein-Hilbert term is again going to be a total derivative, and you need to be careful about, let's say, given Shocking-York terms and so on. And in more general theories, you have to take into account, let's say, all higher derivative boundary terms as well. So understanding the understanding this calculation from the worldsheet is going to be necessarily a difficult task. It's very difficult because from the worldsheet point of view, from nonlinear sigma model on the worldsheet, we know how to reproduce, let's say, the bulk terms in target space, let's say Einstein-Hilbert kind of terms. These terms can be reproduced from the beta functions of the nonlinear sigma model due to work of Shetlin and Osborne in long time back. And but we don't know how to reproduce the boundary terms from the worldsheet by a systematic calculation, because to reproduce boundary terms you need to necessarily path integrate over string fields which preserve the boundary condition, which satisfy the boundary condition. So your field space is going to be restricted, and this is a very hard task to hard task in practice. So trying to reproduce uh, the effects of these boundary terms in target space from the worldsheet point of view is going to be very challenging. So that's a very challenging task. So any formalism which is based on an on-cell framework in which you have to get the boundary terms on target space correct is going to be difficult to build. What we can ask for, is that we go a little bit away from on-cell. So you might hope that if you are allowed to do a calculation which is a little bit off-cell, then you might be able to capture black hole entropy just from the Einstein-Hilbert term kind of terms in the target space. Now this is a very well-known formalism, goes all the way back to, let's say, 1990s or even before. This goes by the name of replica trick. So replica trick is the following method. This method says, suppose you want to calculate thermal entropy of a black hole, which is, I am just drawing the radial direction and the Euclidean time direction, and there is a transverse sphere which I am not drawing in this photograph. So we want to calculate entropy of this black hole, but instead of doing this calculation, we do a different calculation which involves an off-shell geometry of the following form. So this is the geometry, this is the perfect on-cell geometry of the black hole. This is the geometry which looks just like the black hole all the way near the boundary, but as we go at the tip of the cigar, so the location of the cigar in Lorentzian coordinates corresponds to the location of the Lorentzian horizon. So at the tip of the cigar, we change the geometry a little bit. We change the geometry by introducing a conical deficit of strength delta, which is a very small number. And so we do this calculation. This calculation has certain advantages. First advantage is that, note that in this calculation, since the asymptotic boundary in both the geometries are the same, therefore any contribution from boundary terms on the asymptotic boundary is going to cancel between these two terms. In other words, if we don't have the boundary term, then this calculation is perfectly fine. It does not depend on the boundary terms such as given Hawking-Chiok term. You might worry that what happens near the singularity at the tip of the cone here. Well, this method, if we go through this method in details, then we will see that we are instructed to not introduce any boundary term from the tip of the cigar. So this calculation, on the other hand, at the tip of the cigar of the on-cell geometry is perfectly smooth, so you don't get any boundary contribution from the tip of the cigar. So as a summary, this method has a beautiful advantage. The advantage is that now you don't have to reproduce Gibbons-Hawking-York term, but this method is a little bit off-cell because we are introducing this conical singularity, so the geometry is going to be a little bit hard to tackle. So here we are seeing a trade-off. So from the worldsheet point of view, if we can implement this method, then probably we'll be able to reproduce the thermal entropy of black holes, but that might be a little bit challenging from technical point of view because we have to do an off-cell calculation, including this conical singularity. So topic of today's talk is to try to set up this calculation in a trackable example and trying to convince you that this example might give you results which matches let's say target space expectations. Now that we have set up the first question is, in which background are you going to do this calculation? First thing that comes in mind is probably ADS3 string theory with pure NS-NS flux, because then you have a well-controlled worldsheet theory in RNS formalism. Well, we can look into that calculation, but for the purpose of today's talk, I am going to restrict to an even simpler setup. The simpler setup that I am going to look at is going to be Schwarzschild black hole in large D. So for Schwarzschild black hole in large D, we have certain simplifications that I am going to mention here. Let's make some simple observations. So for purpose of today's talk, I am going to set string length to 1, and the metric for a Schwarzschild black hole takes the following form. This is the familiar form. Now note that the radius of the Euclidean time circle is given by 2r0 by d. This formula says something very important. If we are working in d going to infinity limit, then even if we are at string scale temperatures, that is, even if capital R is order 1, we are going to have the radius of the horizon is pretty large. It scales with d. Therefore, if we are interested in leading order in large d dynamics, then the transverse sphere at the horizon can be treated classically. So the nonlinear sigma model on the transverse sphere at the horizon is very large. So you might hope that you might be able to get away with the stringy dynamics only in the radial direction and the time direction, and you can treat the nonlinear sigma model classically. So that's a simplification that you might hope. Now, you might also hope that if the temperature is sufficiently low compared to the string scale, namely, let's say if capital R is much larger than 1, then you might think that the entropy of the black hole is coming from the near horizon area only. So you might like to zoom into the near horizon region of the Schwarzschild black hole in large D. One way to go to the near horizon geometry is the following.
Could you slow down a little bit and try to explain why what you wrote is d going to infinity, r is equal to 2r over d. So right. Big R goes to 0, not to 1. No? I'm kind of lost.
Sorry. So this formula that I have written is going to be valid for any generic value of d. Now, what we are saying here.
So what is big R? What's the definition of big R? Is just 2r 0 over d?
No, so physically this capital R denotes the radius of the Euclidean time circle. So the physical definition is the radius of the Euclidean time circle. That's capital R.
Euclidean time circle. So that, how does it follow from that formula for the Schwarzschild black hole metric?
Yes, so from Schwarzschild black hole metric, we can calculate this radius, and that's capital R, and it's given by 2r0 by d.
Because you expand this function near the horizon.
Yes. Okay, then you're saying that radius, that capital R will appear in front of the spherical part of the metric, right?
Yes. So let me write a little bit more about.
Could you write down the whole metric? Yeah.
Sorry. I write it. So this is the full Schwarzschild metric. Now note that the radius of the transverse sphere at the horizon is controlled by r square. And in this metric, the location of the horizon is at r equal to r0. So r equal to r, so radius of the horizon at the horizon is given by r0. And what we are saying is that in this talk, we will keep the temperature of the black hole fixed as we take large d. So temperature is controlled by capital R. We are going to take the large d limit, keeping the temperature, namely capital R, fixed. So if we look at the leading order dynamics, then we can see that R0 has to be very large, even if we are looking at string scale temperatures. So we are looking at very high temperatures, and still the transverse sphere is very large. That's the point I'm trying to make here.
Okay, so then the second question is, when you say string theory, as we know, string theory requires dimension to be fixed, or you should have some linear dilaton in some direction.
Correct. This is a very important point, and I'm going to come to that. So we are going to take further limits, and we will come to that. So we need to have some time like linear dilaton, but I will discuss in what limit we might expect the results are independent of that. So we'll come to that in a minute. Thank you for the question. Okay, so now we are taking large D limit for holding the temperature of the black hole fixed. So in this limit, we have made an argument that probably we can treat the transverse sphere sort of as a classical sigma model and focus on the stringy dynamics in radial direction, radial and Euclidean time direction. So with that hope in mind, we are going to look into the transverse, we are going to focus on the radial dynamics. And we also said that physically, this is a heuristic picture people have expected for a long time, that the black hole entropy in some sense should come from the near horizon dynamics. Well, this statement should be true at least at low enough temperatures compared to string scale. So with these two intuitions in mind, we are going to focus in the near horizon geometry of Schwarzschild black hole. Now, what I am doing here is a very specific example, Schwarzschild black hole, but this limit can be taken in various black holes far away from extremality, and the resulting near horizon geometry is going to be sort of unchanged. So it's kind of an universal behavior. Although I'll not get into those discussions in this talk, but there is some sense there is a universal behavior in near horizon geometry for non-extremal black holes. So let's define some coordinates which are tailor-made for looking into near horizon region. So I'm defining this coordinate system r hat by this formula, and we are going to focus on dynamics for r hat order 1. Now what does that mean? Let's look at this formula at very large distances. Then this formula can be solved like the following. Note that what it really means. So this factor here, this factor is the same as capital R. We are holding capital R fixed as we are taking large D limit, and we are looking at distance scales of r hat order 1. So we are basically, whereas r naught is order D as we discussed previously. Therefore, what we are saying is that the horizon is big and we are focusing on a dynamics on a very small thin region near the horizon. That's the place where we can expect some simplifications. And one can readily see that if you take the Schwarzschild metric that we have written above and simplify in this limit, the metric takes the following form. So let's look at only the r and t part of the metric. One can see that the metric looks like the following. The metric in fact takes the familiar form of cigar geometry. This metric is the metric of the cigar geometry that is familiar from, let's say, discussion of C equal to 1 strings. Now, what we see here is that because of this simple near horizon geometry, we might have a hope to build the worldsheet theory exactly in this limit. Now, in general, you need to take care of other fields apart from metric. For example, you need to take care of the dilaton. Now, see, we are forgetting the transverse directions. We are going to deal with the transverse sphere as a classical object. Therefore, the dilatons are related by a non-trivial equality, namely by dimensional reduction on the sphere. So you might expect that the way you should relate the linear dilaton in two geometries are the following, where capital phi here, this is the linear dilaton in near horizon cigar geometry. This is the linear dilaton in large D. This is the area of the transverse sphere. This is the area of unit sphere, and this is the radius. So you might hope that if you have a dilaton, which we'll have in a moment once we look into alpha prime corrections, non-trivial dilaton, then you have to relate these dilatons in the near horizon two-dimensional geometry through this formula. So this is a very reasonable expectation. Now with these expectations, you might think that, well, the worldsheet theory is the well-known SL2R by E1. Worldsheet theory is given by SL2R by E1 WGW model. This is the worldsheet theory with which we might hope to build an exact model for this large D black hole. So as it is pointed out earlier, that to build a worldsheet theory, we have to match the central charge. Now, how do we do that? So the central charge of the SL2R by U1 is given by this factor. This is basically, it looks like this. And then we have a non-trivial central charge coming from the sphere at the horizon. So note that the sphere is still curved. Sphere is not a conformal field theory, but it has a lot of directions. So we have to be careful while calculating its central charge. It's not just the flat central charge because it has a curvature and a lot of fields. We have to take care of that. So that's this factor. And one way of working with this is going to be adjusting the level of WGW model K such that the sum of these two central charges is still given by capital D. Let me explain this for a minute. Note that the right hand side is independent of R0. R0 is what determines the temperature of the black hole. Therefore, the central charge of the R and T part and the sphere part is independent of R0. This helps because, as it is pointed out, that we need to add something like a timelike-Liouville theory to get the right central charge. So central charge of timelike-Liouville theory is going to be 26 minus D for us. Advantage is that this timelike-Liouville theory is independent of R0 because of this condition. Since the timelike-Liouville theory is independent of R0, as long as we are looking at vertex operator, so we are going to discuss some dynamics on the worldsheet. Let's say we work with vertex operators, which are, for instance, is going to be entirely in the space-time part. So this is the part I am going to call space-time. So
can I ask something?
yes.
Well, first, you somehow started with Schwarzschild black hole in D dimensions, which is solution of Einstein equations.
Right.
Now you're somehow jumping to some exact CFT. You wrote level K, so that's presumably including alpha prime corrections.
This is
so somehow, so your Schwarzschild large D solution is just indication of what you want to get. So
good question. I'm going to. So we
can I ask? Yeah, one more question, which is maybe more important. Your Euclidean time is periodic.
Correct.
Well, you want to add time like dilaton, which is linear in time.
Right.
How on earth you're going to combine these two facts, periodicity in time and linear dilaton in time?
Right. I'm going to deal with both the facts one by one. So give me like 5 minutes. I am going to deal with these. Both of them are very pressing questions, and I'm going to say something about them.
Okay.
So
thank you.
First, let's deal. Thank you for the question. So first, let's deal with the question about time like linear dilaton and how we are going to tackle that. And then we come back to the other question. So what we are saying here is that so far the Schwarzschild solution was the leading order Einstein gravity equation solution, and this is one attempt. So this is way one of defining alpha prime corrections, and we'll come to way two and we'll talk about that. So within way one, we have to deal with this timelike-Liouville theory. So the proposal is the following. Suppose we are interested only in vertex operators which are within this SL2R by U1 and maybe on the sphere. So my vertex operators are going to be only in this part. And if I am going to calculate only in classical string theory, that is if we take G strings going to zero limit first and then take D going to infinity. The reason we are doing this is that since we are looking at classical string theory and my vertex operators are entirely contained within, let's say, SL2R by U1, if this is the setting, then the timelike-Liouville theory that we are adding is going to be an overall factor because my vertex operators are insensitive and I am doing my entire calculation is on the sphere. Therefore, any dependence on the timelike-Liouville theory is going to be an overall factor. And very importantly, timelike-Liouville theory is independent of R0. Therefore, this overall factor is going to be independent of the temperature of the black hole. So since it's going to be an overall factor, as far as we are interested in classical string theory in d going to infinity limit, and my vertex operators are entirely in the black hole region, my calculations can be reproduced by in target space. One might hope to reproduce, and I'll present evidence. So one might hope to reproduce this calculation from a target space effective action only in d space-time direct dimensions. So as long as we are not exciting the Liouville, time-like-Liouville theory degrees of freedom, the dynamics might, and in classically, the dynamics might be captured by a d-dimensional effective action. So let's make this picture a little bit more precise and answer the second question as well. So what is this target space effective action that we might hope to write down that will capture the dynamics in a specific limit of interest? One way of writing down a target space effective action is to take the effective action for bosonic string theory and just pretend that we are in d dimensions. So this is a very ad hoc thing to do, and Callan-Myers-Perry has already done it in, let's say, 1980s, late 1980s. So this ad hoc thing is going to give us something sensitive. So I am going to write down the effective action of bosonic string theory, including metric and the dilaton only up to, let's say, first order in alpha prime. It takes the following form. Now, note that we can discuss alpha prime corrections to Schwarzschild black hole that I mentioned above using this effective action. So now we have two different ways of defining alpha prime corrections. This is the way one, where we say that we replace the worldsheet theory with an exact SL2R by U1 WGW model and compute alpha prime corrections. That's one way of defining alpha prime corrections. And the second way is to use this effective action in target space and trying to calculate alpha prime corrections. These alpha prime corrections are easy to calculate and people have already calculated it. So now that we have two ways we can ask, are they equivalent? So when I say alpha prime corrections, my entire talk is always going to be classical string theory. So always going to be G strings going to 0, and the alpha prime corrections that we are looking at are all going to be in D going to infinity limits. So leading order in D going to infinity limit in classical string theory, when you calculate alpha prime corrections by these two methods, one can readily see that they match, at least up to first order in alpha prime. This calculation is already done. And
excuse me, can I ask one question? In the first way, how do you relate your string to a black hole, to Hawking temperature? Is it some relation between central charge and the temperature?
Yes, sorry, I should write the formula explicitly. So if you try to solve this equation, the solution of this equation is the following. The radius of the black hole. So let me write down the solution first. So if you try to solve this central charge equation, you find that the level of the WGW model is given in terms of the inverse temperature of the black hole by this formula. Note that if we are at low enough temperature, that is 2 R0 by D is much larger than 1, low enough temperature compared to string scale, then this formula just reduces to the formula we had before. So we have seen this formula before here. So we have seen that the inverse temperature of the black hole is given by 2 R0 by D. What we are seeing here is that this defines a way of extending it, including alpha prime corrections, and this is the well-known cigar geometry. So people who studied this cigar geometry, people also studied settling, Kazakov settling. People also studied alpha prime corrections to this cigar geometry systematically, order by order, and one can discuss that in a suitable let's say standard framework. There is some standard regularization scheme. You can study these corrections and one can see that the temperature of the cigar geometry with alpha prime corrections is still given by square root of k.
So basically you consider a string on the cigar, and you require that it is self-consistent. That
Yes, yes,
okay? Thanks.
yes. So this is how you define this this way of defining alpha prime corrections. And then now we are getting back to this question about, are these two ways same or not? Now, to the extent we can discuss. So first method is applicable. We can do exact calculations, because exact calculation to any order in alpha prime, whereas second way is much more perturbative. So let's try to see the equivalence only at the level of first order in alpha prime, where the calculations can be done. And it turns out that they exactly match. This calculation can be checked by going to this Callan-Myers-Perry's work in 1980s and taking the limits that we are discussing. And one can see that the metric in both directions just match without any effort. So there is nothing to discuss, including first alpha prime correction. That's very important. We have checked it, including first alpha prime corrections. But there is something much more interesting going on when you think about the dilaton, because now you are going to have a non-trivial dilaton sourced by the R squared term. So you can still see you can see that the alpha prime corrections that you obtain from the cigar geometry using the methods of C equal to 1 strings, let's say, those alpha prime corrections match with the alpha prime corrections that you get from large D black hole using this effective action. So these two methods gives us confidence that probably the worldsheet theory that we are looking at in terms of this exact sigma model, as far as the black hole degrees of freedom are concerned, as long as you don't excite the time-like-Liouville theory, and we look at classical string theory, but with all order in alpha prime corrections, we are good. We are probably going to discuss just the black hole physics. Now, this is the expectation.
Could you say where there is a difference between what Chen and Maldacena were discussing? I recall they discussed also large D.
Right.
And they were, right. Yeah, maybe you could comment on that. Yeah.
Yeah, this is also, yes. So let's just focus on what are the differences. First of all, I did not mention kind of references. So first of all, the classical dynamics of black holes in large D, that's like, let's say, Emperor and friends. They try to discuss it to a great amount, and the universality that we are talking about in the near horizon region is pointed out by them. And then let's say the precise version of the first method that we are discussing, and its comparison with second method, is because of Singh and Maldacena. What they did is that so far what we have discussed is precisely what they pointed out. So far this discussion is basically a review of what they pointed out. Now we are going to get into more interesting questions in a minute, and I'll mention what are the new contributions from my work in a minute. So far we have reviewed this discussion. Now we are going to use this discussion to make some explicit calculations. Now, one thing to note about this black hole is that there is also winding condensates. So far we are talking about perturbative alpha prime corrections, but then there are also non-perturbative in alpha prime winding condensates. So if you have this black hole, let's say that you have a spherical black hole of radius r0, typically you are going to have a winding condensate which condenses within a very thin domain. So in our discussion, R0 is order D, whereas you are going to have a thin domain of this length D by 2 R0, where the winding condensate already condenses. This is the important fact. This is new and our contribution, and let's try to discuss this in a little bit more details. So how do we understand what is the thickness of this cell? One way of going about it is the following. Suppose I take the effective action written here, and we try to discuss when does alpha prime corrections become significant as seen by an observer far away from the black hole. So if you are sitting very far away from the black hole, probably this winding condensate is not going to affect your geometry mass, and we can ask, how does the geometry look like very far away from the black hole? And we get the following formula. Let's say we are very far away from the black hole, then the geometry looks like the following. Where this radius of stressed horizon is given by the following formula. This can be calculated because we have the effective action. So this calculation is precise, and we get this formula. So if we take the alpha prime corrections, then we see that it seems like alpha prime corrections take over as seen by an observer at infinity. The alpha prime corrections take over at stressed horizon, which is little bit outside the horizon, the naive horizon that you see. So this is the same thickness. So the thickness here is the same thickness that I have written here using the map that I presented before. So now you might think that, well, this is the part where non-trivial alpha prime corrections take over perturbatively. Is there a sense that even winding condensates are localized within the same radius? It's not necessarily have to be the same, but in a minute we will discuss the vertex operators for winding condensates, and we will see the following. We'll see the radial dependence of the winding condensates also take the following form. Now, let me remind you the map of the observer at infinity. So, for an observer at infinity, the map between the radial coordinates is given here. From this, you can see that if you set r hat is 1 by k minus 2, so this formula just says that the black hole is extended until r hat equal to 1 by k minus 2. So r hat is roughly the distance from the horizon. So it tells you that even the non-perturbative winding condensates are extending up to the same distance scale. So this is the length scale which we will call the stressed horizon, up to which the winding condensates are extended. Now, because winding condensates are extended outside the horizon, you have to be very careful to say anything about the horizon itself, because you need to take into back reaction of the winding condensates. So far in this discussion that we presented in this effective action, we did not add the back reaction of the winding condensates. And we have to be careful about how to introduce winding condensates in SL2R by U1 picture as well. So let me get into that. How to take into account the winding condensates on the worldsheet. So the worldsheet theory, so this is where we come to FZZ type duality in the context of SL2R by U1. So let me try to say a little bit about what this duality is. So the worldsheet theory, so one way of building the worldsheet theory is to take the metric and the dilaton, and perturbatively you build the nonlinear sigma model. Those are the perturbative in alpha prime corrections. Now we also have winding condensate. So one way of building this worldsheet theory is going to be given by the following. If we are very far away from the cigar geometry, we kind of see a cylinder. So the cylinder has a radial direction. So the radial direction, I'm writing phi here. So radial direction is written as phi. And we have a non-trivial linear dilaton where q is given by 1 by square root of k minus 2. This takes care of the central charge of the theory. And we have a compact direction, namely the Euclidean time circle. So this is the free theory on the cylinder. And we can add the winding condensates to it. So what we can do is write down the following action. So where the winding condensates are given by the following formula. And the coordinates, if you want to relate to the old coordinates, then phi is going to be given by r hat, and tau is going to be given by square root k times tau hat. Now, note few things about this formula. First of all, this is the radial dependence that we were talking about before. So what we have done here is, in this action, we have taken into account only the contribution of the winding condensates. Let's make this more clear by first going back to a simpler setup, namely Liouville theory. And in Liouville theory, we will try to understand. We have similar phenomena in just Liouville theory, and then we come back to this worldsheet theory and try to understand this theory better. So the Liouville theory is given by the same action, just the interaction time is little different. So in Liouville theory, we have two interaction terms. One of them is e to the power 2b phi and the other one is e to the power 2 by b phi. This is very important. For instance, suppose you want to write down the correlation functions of vertex operators given by e to the power 2 alpha phi, then one can see that these correlation functions have poles, and those poles are given by the following locations. For n and m takes values in this lattice. So if you are dealing with Liouville theory, ignoring this second term in the interaction, then you will produce only half of the residues. You are not going to get all the residues of the correlation function. So it's very important that you take into account both the interaction terms to reproduce the exact set of poles as expected from DOZZ formula in Liouville theory. Note that if you are doing a perturbative calculation, let's say b going to zero limit, if you are discussing Liouville theory in b going to zero limit, then you will be dealing with this interaction term, whereas this should look like non-perturbative. So in a perturbative calculation, you might tend to avoid this other interaction term, but it's very important if you want to get the a consistent conformal field theory built out of Liouville theory. Same sentence is true in our discussion. This is a Liouville-like theory. It has features like Liouville theory. So what happens if you take vertex operators in our worldsheet theory and just keep the winding condensates here alone? Again, you are going to have residues. You are going to produce certain number of poles of the correlation function, but you are not going to produce all of them. This is the one way of thinking about it. You should think about, let's e to the power 2b phi is the analog of the winding condensates. So if you want to reproduce all the poles in the correlation functions, you need to take the perturbative worldsheet theory given by the metric and dilaton, and you also have to take into account winding condensates. So the worldsheet way of saying that you are going to take into account back reaction of the winding condensate means that you add both the vertex operators on the worldsheet.
Could I ask you something? So you somehow you introducing, so you're assuming you have string mode wrapped on the circle, and with this winding mode you represent as a vertex operator added to the action. It's kind of condensate of this mode. Why? What do you want to do with this? It will contribute to the entropy. What's the motivation for doing this? Why you want to deform your...
We are forced to do it. So if you are thinking about the physical picture, then the winding condensates are basically tachyonic near the horizon. So they will try to condense. So the sensible thing is to take the condensed picture. So you need to take the back reaction of the winding condensates because they are tachyonic near the horizon. And this tachyon survive. If you have superstrings, still they will survive. So first of all, this is a physical picture that we want. Because they are tachyonic, you need to condense them. And the second picture is from the point of view of the formal worldsheet theory. So from the formal worldsheet theory, just like in Liouville theory, if you just kept, let's say, e to the power 2b phi, you would have missed something. So if the Liouville theory is defined by a Lagrangian in which you omit the second term, then the free field calculations are only going to give you half of the poles of the exact answer.
Yeah,
So
but just a second. So there's nothing a priori wrong with just starting with cigar conformity theory. So what is wrong with that? So if you just start with cigar itself, it's a conformity theory by itself. So why you want to deform it further by this winding condensate? I'm just trying to understand the logic of
right. So
where are you going?
if we think about cigar conformal by cigar conformal field theory, if we mean SL2R by U1, so SL2R by U1 can be defined formally. We can compute its correlation functions, let's say formally. Now, so only claim I am making is that those answers are going to have, let's say, poles parameterized by 2 integers. And if you want to do Lagrangian based calculations to reproduce those poles, then you need to have winding condensate and the metric and dilaton. So it's the similar sentence in Liouville theory. If you think about Liouville theory and axiomatic conformal field theory, then DOZZ formula is going to give you poles, which is parameterized by 2 integers. But if you want to reproduce them using a Lagrangian, then you need to keep both e to the power 2b phi and e to the power 2 by b phi. So I'm just saying that the formal conformal field theory requires you to take into account both the winding condensates and metric and dilaton. This is something that we looked into similar phenomena for SL2R by U1 in NSNS. For ADS3 with pure NSNS flux, the worldsheet theory is SL2R by U1, and in which we checked the similar phenomena in one of my papers. So I'm not saying that we are changing the conformal field theory. I'm saying that to reproduce all the features of the conformal field theory from the worldsheet, we need to have the winding condensates. That's the only way of consistently getting everything correct.
Is that somehow related to the fact that you replaced the coset by just cylinder? Because here you just have flat.
Right. So replacing the coset by the cylinder is wrong. So if you want to correct it, then you have to add corrections to it. I'm saying there are 2 sets of corrections. One set of corrections is given by these winding operators, W plus and W minus. And there are other set of corrections which will come from the metric and dilaton.
Okay.
So we are still dealing with the exact coset. Thank you for the questions. These are very important questions. Thank you. So now that we kind of understand the worldsheet theory, we would like to do some calculations. But before we proceed to do some calculations, we need to be very careful about cosmological constant term here. How do we fix it? Well, oftentimes people say if you shift your field phi by a constant, let's say shift by constant, then you will change the cosmological constant. While that is true, this will also change the G strings. It will also change the definition of G strings. This is related to the fact that in target space, phi is basically the radial direction. And what you are doing is that instead of fixing the coordinate system, you are changing the definition of coordinate system. Therefore, your horizon in the new coordinate system looks like in a different place. So if we fix the coordinate system in target space, namely, let's say we fix the notion of radial coordinate system, a horizon is given at R0, then that should stop us from making any coordinate transformations like phi going to phi plus constant. So with that definition, we can give a meaning to the cosmological constant that appears in this axiom. One way of giving meaning is the following. One can say that, so one way of giving meaning to this cosmological constant is going to be the following. But can I know how much time I have left? Because
it's roughly 10 minutes, yes.
Okay. So then I'm not going to get into the details of fixing this cosmological constant. Rather, I'm going to get into the main punchline of the talk. So far we have discussed the on-cell black hole geometry, which is given by this, diagram. Now, For the off-shell calculation that we are set out to do, we also have to introduce a conical singularity at the tip of the cigar. Now, how do we do it on the worldsheet? That's a very important question. Now, the motivation, the way of thinking about it comes from understanding the cigar geometry in target space. So one can ask how to reproduce the thermodynamics of the cigar geometry by doing a calculation of the on-cell action or free energy. This is a calculation, again, goes long time back, around 2003, let's say. The idea is the following. The idea is that you take a cut-off surface, so you cut off your cigar geometry at some radial distance, and then you fix the G strings on the radial surface while changing the temperature. So that's the prescription we are going to mimic on the worldsheet. On the worldsheet, what we are going to say is that we are going to change the temperature. So temperature is controlled by K. So we are going to change the temperature a little bit. This includes changing the winding condensates. So my winding condensates with this shift, are going to look like a little bit different here. And with this new winding condensates, I'm going to do the calculation while not changing the linear dilaton. Since we are not changing the linear dilaton, we are going to find ourselves in an off-shell geometry. So one way of introducing the conical singularity is by changing the temperature and along with suitable, dilaton on the tip of the cigar, such that we change that a little bit and then presume that the temperature is not changed at all. So this picture is going to give us a geometry which is going to be off-shell and in particular going to have a conical singularity at the tip of the cigar. So the calculation that we are suggesting for the off-shell geometry given here is the following. We take the same action as given here and just replace the winding condensates with this modified winding condensates here. So this is again a calculation that can be done. Now, once we have both the calculations, we can plug them back into our formula for entropy and calculate the entropy of the black hole. Since I am highly constrained by the available time, I'm not going to get into the details, but I am rather going to write down the final result and then try to discuss some of the implications of the formula. I hope the method is clear to the audience, and here is what we find after calculation. So this is the radius of the Euclidean time circle, and this is the entropy calculated by this method. Now, here is the Haggerand temperature of flat space. And this is the Haggerand temperature of the cigar geometry. The entropy, so the ratio of entropy, where S is the entropy calculated from near horizon geometry. Let me write it as near horizon. So the entropy is calculated from near horizon geometry is SNH. S naught is the standard Bekenstein-Hawking entropy. So S naught is given by, let's say, standard Bekenstein-Hawking entropy. We see that at low temperatures, so if we are in this domain at very low temperatures, as we take alpha prime corrections into account and as we increase our temperature, the ratio is increasing a little. Now, this can be checked even using alpha prime corrections to the effective action that we presented before. So first alpha prime corrections to thermal entropy can be calculated from this effective action. And one can see that that answer also has a similar effect. Now, our calculations, our formula reproduce the precise first alpha leading order answer and first alpha prime correction exactly. So the exact answer for near horizon geometry takes the following form. It's S naught and then a factor of k by k minus 2. This factor is related to replacing R0 with RSH. So if you replace this factor, you will get this additional term. And the details of the calculation, which I did not get into, gives us some factors, which I'm just writing here blindly pretty much. So this is the answer we get from the exact calculation that we mentioned. First alpha prime correction is first 1 by k correction from this answer, and that reproduces the answer from Callan-Myers-Perry. On the other hand, note that this formula is valid for all values of k. Therefore, we might hope to learn something about string scale temperature, namely near Hagedorn dynamics. This calculation was based on near horizon geometry, and therefore this calculation is not going to be able to capture the features far away from the horizon. For example, if we are near the Hagedorn temperature of flat space, which is given by RH, then there is a winding condensate that develops in far away region, and contributions of this winding condensate to large D black hole is not captured by our calculation. So our calculation should be taken seriously only within this domain, as far as large D black hole is concerned. However, our calculation remains the same if we are interested in the cigar geometry. If we are interested in the 2D cigar geometry, then this calculation can be taken seriously until all the way to RHC, which is the Hagedorn temperature of the cigar geometry. And we see that the entropy essentially vanishes because of this factor. So because of this factor, and remember that square root k is capital R, because of this factor the entropy vanishes as we go near the Hagedorn temperature of cigar geometry. Now this is related to black hole string transition. What we are saying is that our calculation was a classical string theory calculation. So this vanishing of entropy near Hagedorn temperature basically suggests that 1 by g string square contribution goes to 0. This is related to the fact that the black hole is turning into a string and the entropy is essentially smaller. One can ask similar questions within KKK matrix model. Within KKK matrix model, one can again ask what happens to the entropy as we approach the Hagedorn temperature, which in KKK language is going to be temperatures higher than KT transition temperature. And there are evidence from in recent literature that again the 1 by g string square entropy goes to 0. So these two facts are similar from our calculation and the calculation that we find, let's say, in KKK matrix model. And intuitively, we also expect such a feature. We expect that if the black hole is turning into a string, then the leading order entropy is to vanish, so that the entropy is getting smaller and smaller. We reproduce these features by a complete worldsheet calculation, and this formalism of worldsheet is also we can take time dependent perturbations to our formalism very easily into account. So we have full control to discuss any time dependence dynamics around the black hole, including alpha prime corrections, which would be very interesting to do in the future, including generalizing this discussion for various charged black holes. For charged black holes, similar calculations can be done, and trying to match their alpha prime corrections using this method would be very interesting. So I'm happy to answer questions, or otherwise I'll stop here because I'm running out of time.
Yeah, I have a question just to understand better. So you just said that your result matches the first alpha prime correction, but from effective action point of view, you don't have any winding mode there. You didn't introduce a field corresponding to winding condensate into the effective action, target space effective action.
Right, but from target space effective action, these are non-perturbative in alpha prime corrections. So
yes, but so you're saying if you just ignore this non-perturbative correction, then you match the leading alpha prime correction as 1 over k correction here. Is that right? So what could you explain what you meant by saying that your result matches leading alpha prime correction from effective action point of view? So that's ignoring this winding condensate, right?
It's a very important point. Yes. So on the target space, you might say that on the target space you have ignored the winding condensate. So is that calculation correct, or what is the right calculation? Because if you take the winding condensate into account, then in target space you don't have the horizon. Before that you get non-trivial correction. So what it means to do a target space calculation in terms of area of the horizon. So this observation that we make is indeed, but the calculation we did is a formal conformal field theory calculation. We are forced to introduce the winding condensate because we wanted to have all the residues. So the only calculation in terms of conformal field theory that we can do on the worldsheet is the one that we did. Now, it's a nice observation. It's a nice observation that it reproduces the target space answer based on ignoring the winding condensate, at least up to first order in alpha prime corrections. Now, it might or might not reproduce, probably perturbatively it will reproduce until certain orders, we don't know. But there is no reason to believe that it should match all the way near Hagedorn temperature, because then the winding condensate is definitely very important.
So another question, you mentioned at some point FZZ, Fateev, the homological duality. Did you actually use it, or what was the point?
We definitely, so the entire idea is from there, right?
Yes.
So
how did you use it? So I just kind of missing where the link. So you're just using it when you talk about Liouville theory, or?
No. We don't do the calculation in Liouville theory. We do the calculation in this theory, right? So I did not tell you the calculation in detail. So the calculation we do is basically, so what we are saying is that in Liouville theory you have a self-duality, which is B going to 1 by B. Now in the theory that we are looking at, so the nicest way of looking at FZZ duality should be similar. We should be able to say that there is one conformal field theory. It's a kind of a self-duality. That's what we are saying. So we are just saying that the FZZ duality, which is usually said as a duality, so from the point of view of the conformal field theory, it's just a self-duality, just like in Liouville theory. It's not a strong duality which maps one theory to other. It's just a self-duality. And this picture, which is FZZ, so we also extended this FZZ type duality in ADS3. In ADS3, this is a little bit surprising, because in ADS3, the analog of FZZ duality would say that we have a winding condensate picture of the BTG black hole. Now, BTG black hole is a large black hole. So for a large black hole, we don't expect this winding condensate descriptions usually. This winding condensate descriptions in target space corresponds to, let's say, Horowitz-Pulczynski type solutions, which are like small black holes. So this FZZ duality, when interpreted in ADS3, actually gives you something kind of, in my opinion, remarkable. It gives you the winding condensate picture for the large black hole, which is conceptually different from the discussion that we had right now. Right now, we looked at a flat space black hole. So flat space black holes are like small black holes in ADS point of view. So this picture is conceptually fine. It's like Horowitz-Pulczynski type discussion in some sense. That in ADS3 we extended it, and that has a different meaning.
Okay. Thank you.
Yeah. Thank you.
Any other questions?
Thank you for all the questions.
Yeah, okay. It seems that we don't have any other questions.
Thank you for the talk. Yeah, thank you. Thank you much. Yes.
Thank you.
Okay, thank you.
Bye.